Okay, now we're going to take a look at what happens when we're given a right-angled triangle and we're given information about the three sides. Anytime, hear me, hear me, hear me, hear me. Anytime you are given the length information about the length of three sides of a right-angled triangle, it's likely you're going to use Pythagorean theorem. Okay, so I want to make sure that you guys first even understand Pythagorean theorem, and I can't remember if I've talked about this in a previous video, so I'm just going to do it right now. Think of it this way. Back in the very, very, very olden days, there was this kid in Greece named Pythagoras, and he was playing on the beach with a bunch of right-angled triangles. I'm sorry, he was playing on the beach with a bunch of squares. I already messed up the story. He was playing on the beach with a bunch of squares. So he had a square that was 3 by 3. He had a square that was 1, 2, 3, 1, 2, 3. I know it looks like a rectangle, but let's just pretend it's a square. This was 3 by 3. Of course, squares have the same length and width. This was 4 by 4. You guys must be wondering about me today. Okay, 4 by 4. And then he had another square that was 5 by 5. And he found that when he put them together, he found that the 3 by 3 square, the 4 by 4 square, and the 5 by 5 square, that when they put together, there was this triangular hole in the middle. And every time he put the 3, 4, and 5 together, he always got a right-angled triangle. Here, I'm just going to shade it inside the triangular hole that's inside these squares. And he found, wait a minute, when I do this with a 6 by 6, actually let me do it here, a 6 by 6, and an 8 by 8 triangle, and a 10 by 10. I'm running out of space, 10 by 10. When I do this with a 5 by 5, and a 12 by 12, oh, that's totally not a square, excuse me, and a 13 by 13. When I do it with a 7 by 7, and 24, again, not a great triangle, square, 24 by 24, and 25 by 25. Holy cow! I keep on getting these right-angled triangular holes each and every time. What is the deal? And then he realized there was this pattern. He said, if you take a square and you count up all the squares in here, which of course a 5 by 5 square, 5 times 5 is 25. 4 times 4 is, there's 16 little squares in here, and 3 by 3 is, there's going to be 9 little squares in here. But every time the number of squares in this big square added up to the number of squares here plus the number of squares here, each and every time the triangular hole had a right angle. And that is Pythagorean's theorem. And this is a picture of a square. And in math, this is notation, handwriting of a square. So when you have a square that's A by A, and you have another square that's B by B, and you add those little squares in the big squares together, you will always get, if this adds up to C by C, you will always get a right angle triangular hole in the middle. This is Pythagorean's theorem. So now I hope you understand it better, and now let's use it every time we see information about the three sides of a right angle triangle, because we know that the two sides that make up the right angle, when we add their squares, they will equal the square of the side opposite the right angle triangle, right? Opposite the right angle triangle is the one that's on its own, and the two that make the right angle, Those two we add together. So then, once we have that, we have a relationship. And now if the question is solve for x, we can solve for x, which is 2 squared is 4, x squared is x squared, 8 squared is 16, 10 squared is 100, and now let's solve. So we have 4x squared equals 100 minus 16. 4x squared equals 84. X squared equals 84 over 4. X squared equals 4 goes into 8 twice and 4 goes into 8 once. And now we're wondering, something squared is 21. Now, it would be nice if it was 9, 16, 25, 36, 49, 64, 81, 100, 121, 144, and so on, a perfect square number, but it's not. So we just have to answer the question the way we know, which is, if something squared equals 21, then x will be plus or minus the root of 21. Just like if x squared is equal to 9, x will equal plus or minus 3, plus or minus whatever the root of this is. If you can take the root, great. If you can't, you just write the root of what you can't take the root of evenly. Like, you can obviously do this in your calculator. You know that 21 is in between the perfect square of 16 and 25. So if the root of 16 is 4 and the root of 25 is 5, you know that this is equal to 4 point something, something between 4 and 5, but you don't know exactly what it is. So, and seeing as it's not a number that can be broken down to make it a mixed radical, we just leave it as the root of 21.